Hello everyone, my name is Eve Young, and I'm going to have a walkthrough around one of my most recent projects on building a modern computer from scratch. And this is with the help of a book and online resources called Nan2 Tetrius, which provides the platform and software to help you to build such computer, starting from the very low level circuits to the logic chip, and using one specific language called HDL, which is the hardware description language. We're going to build a set of elementary logic gates like AND, OR, NOT, MUX, and DMUX. After that, we're going to use those chips to build a family of adder chips, and furthermore the ALU, which is the arithmetic logic units, and then from there we're going to build a memory hierarchy from single bit cells to registers, and then to RAM units with arbitrary sizes such as RAM 8, RAM 64, RAM 512, RAM 4K, and then 16K. After having the ALU and RAM, we are ready to come up with a complete computer architecture by combining the CPU and RAM and ROM together. So here we come up with a comprehensive computer named Hack, which includes the CPU, ROM, and RAM all together. And with the help of such computer architecture, we can run low-level interactive programs that are written in assembly language on the given CPU emulator. As for the next step, we're going to focus on the assembler, which helps to translate the symbolic instructions into binary codes that can be understood by the computer we just built. I wrote a Python program, performs like parsing, code generation, and symbol resolution functionalities. So now let's take a detailed look at the Python codes for the assembler. So apparently we have three different modules to use here. First, we need to do a data cleaning that cleans the assembly input file. Next, we're going to use the process label module to help identify labels and get updated codes and update the reference table. In the end, we're going to run the actual translation functionality to help translate new lines into binary codes. Then the next part we're going to have is the VM translator. So for modern compilers to work, it typically needs to translate high-level programs into an intermediate code first, which is designed to run an abstract virtual machine. So I wrote another Python program in this folder, which is kind of like a GRE-like program that translates the push and pop and arithmetic VM commands into assembly code, which can be run on the hack computer we just built earlier. Additionally, the other two critical programming abstractions like branching and subroutines can also be realized, which extends the basic translator into a full-blown VM translator, which becomes the backend for compilers that translates high-level program into VM code. And in the end, we need to work on the compiler, which helps turn the high-level languages like Jack language in our specific hack computer, and to run such a syntax analyzer, like tokenize and parse the Jack code we have using a recursive parsing algorithm, and then turn it into VM code to feed into our VM translator developed earlier. So there's a thoroughly consideration that we need to take to realize all the high-level programming abstractions such as classes, methods, statements, expressions, objects, etc. Okay, that's pretty much everything we need to implement for a modern computer to work. So let's have a quick walkthrough again. We start from building the logic chips, and then using the chips to get our ALU and RAM, and then combine the ALU, RAM, and ROM. We get our full computer architecture, and then on a software level, we write our assemblers, VM Translator and compiler to help realize the whole process from a high-level Jack code to a VM code and then translate it to the assembly code, which can be understood by the computer. And in the end, in order to run and test our modern computer, I wrote a game using the high-level language Jack, which is a simple high-level object-oriented and Java-like language to design a graphical and keyboard control computer game. So now let's do a quick demo on how the game actually runs on the computer we just built. So first, let's take a look at the source code for this game, Diamond Hunter, written in the Jack language. We have several different classes for the game. And in order to get the game actually running, we need to feed our Jack code into the VM translator. And here, write it data, and we have the VM file accordingly. Now let's open up our VM emulator and try to open up the game. Load the program. Okay, now let's click on the run button. Now we have the game interface showing up on the virtual screen with a virtual keyboard down below. And now we can start the game by press P and also control by arrows. Okay, now let's start the game by pressing P. And now you will see you have a diamond shape to the left of the screen. And also in the middle, there are randomly populated placement moving around to catch you. And also we have the target diamond to the right of the screen. Now let's move around trying to get the diamond. Oops. Oops. Oh, that's close. So let's play that again. Play again. Yeah, I guess we got the diamond. So the game is completed. And looks like our game program is running perfectly on our computers. Okay, so that's pretty much everything about building a modern computer and running a computer on a funny game. I hope you have a better understanding of how a modern computer works from scratch. And please let me know if you have any questions on any of the steps, any concepts, any code implementation. I will be happy to let you know more about this. So thanks again and stay tuned for the next video.